Our next speaker, Maureen Raymo, is a paleoclimatologist and marine geologist. She's the co-founding Dean Emerita of the Columbia Climate School and the G. Unger Vetlesen Professor of Earth and Environmental Sciences at Columbia University in New York. She's done a wide range of pioneering work on the origin of the ice ages, Earth's geological temperature record, and sea level change. Today, Maureen will describe climate, CO2, and sea level. Past is Prologue. Please help me welcome Maureen Raymo.
That's not the first one. There's the first one. Well, thank you very much. There's some hard acts to follow here, and especially Jane and Sylvia. I've admired you and your work for decades, especially Sylvia, who really opened up the field of oceanographic research to women and breaking the taboos of having women on research vessels. So thank you for that. It made a big difference in my life. So I'm going to start here with the Keeling curve. There's probably no better place to start. Charles Keeling started measuring carbon dioxide in our atmosphere systematically on the top of Mauna Loa since the 50s. And quite literally, over the course of my lifetime, CO2 levels have increased by 35%. You can see the annual cycle of the biosphere, the northern hemisphere forests, breathing in and out. But that long-term trend is the result of the combustion of fossil fuels and industrialization. Not only is CO2 at 427 parts per million now, the highest it's ever been in human history, the global CO2 emissions are also the highest they have ever been in the last 150 years. And this is despite decades of promises from all the leading nations of the world. So if we change the x-axis on this grant, so the record now goes back to 10,000 years ago, it becomes painfully obvious how anomalous the recent atmospheric trends are, trends that are due entirely to us and our industrialization of our planet. The basic physics of planetary black body radiation and greenhouse gases tell us that the Earth should be heating up. And of course it is. We are. This is NASA's animation of 21 million monthly average temperature observations from over 50,000 weather stations around the globe. And you can see it ticking through the decades. They're not absolute temperatures that are measured here, but anomalies, the difference from the mid-20th century average. This is what 1.1 degrees Celsius of global warming looks like. And you can see that the warming is generally greatest over the continents due to the difference in heat capacity between land and water. And you can also see that warming is amplified at high latitudes by positive feedback, such as the snow and ice reflectivity feedback. And just in case you've been on a media diet these last few months, and you might have missed this, the global surface air temperature anomalies of the last 9 months have been shocking, unlike anything we've yet witnessed. And this is the same data, just plotted in a different way. Oh, I guess the laser doesn't work. And you can see from the 40s up until 2023 and into 2024. That jump in mean annual surface temperatures is crazy. Okay, we're not even sure in the scientific community how to fully explain what's going on right now. So we are now well beyond 1.5 degrees of warming relative to pre-industrial. That was the limit established by the 2015 Paris Agreement as the limit of dangerous anthropogenic interference with the climate system. So, the Earth's temperature goes up by a few degrees. So what now? That's obviously rhetorical after today's talks. But it is a reasonable question for a person on the average person on the street to ask. If I change the temperature in this room by 1 degree, nobody would notice. And even if you were a person that appreciates that most of the risks of that 1 degree of warming, or that 1.5 degrees of warming, is in the extremes, the extreme forest fires, the extreme drought, the extreme rain. We call them the tail risks. And you could see an example of how, right here, about how moving the mean dramatically increases the number of extreme and very hot weather. So even if you appreciate that, you may still be thinking that in a worst-case scenario, we can reverse the consequences of global warming via solar radiation management, which I'm surprised no one's talked about, or carbon dioxide removal. We cannot. In addition to the ongoing extinction of plant and animal species, which is clearly irreversible, one of the most catastrophic consequences of global warming, sea level rise, is also essentially irreversible on any timescale relevant to our civilization, certainly on the timescale of centuries to millennia. And this catastrophe is well underway. The NASA GRACE satellite missions have been measuring the mass loss in the polar ice caps since the beginning of this century. And you can see on the graph on the bottom is telling you the mass loss of the ice in gigatons per year. And it's shown in red and orange colors on the maps of Greenland and Antarctica on the right. And this mass loss is well underway. In Greenland, we can see every year that more ice is lost in the summer than grows in the subsequent winter. And Antarctica is also losing mass, in particular in the West Antarctic Peninsula and West Antarctic ice sheet region. But something very unpredictable happened 2 years ago, and perhaps you can see this in the blue curve at the bottom. And that is the trend in ice loss in Antarctica reversed. Okay? When I saw that data about a year ago, I was gobsmacked. This is due to ice growth, the blue areas at higher elevations and in East Antarctica. And at the time, me and many other scientists were like, wow, that's surprising. And it's especially a big wow because there's a narrative that exists out in the world of climate scientists that says it's a possibility that East Antarctica will gain mass as the polar climate warms, and thus potentially cancel out sea level rise due to melt in Greenland and West Antarctica. Currently, the continent is classified as a polar desert, with temperatures so cold in East Antarctica that there's hardly any snowfall at all. So, a little warmer, a little more snow. That was a reasonable hypothesis. It still is. If we melted all the snow, if we melted all the ice in Greenland and spread it evenly over the ocean, sea level would rise by about 5 meters around the world. The melting of West Antarctica would be about the same, about 5 meter sea level rise. And if you melted all of East Antarctica, sea level would rise by 50 meters. So, how sensitive are polar ice sheets to a few degrees of global warming? And how much can we expect seas to rise as the ice sheets very, very slowly come into equilibrium with the amount of new heat that we have added to the atmosphere and the ocean over the last century? We can look to the past to answer these questions. Evidence of past higher sea levels can be found all over the world. In this picture, you can see the Ningaloo Barrier Reef of the northwestern Australian shoreline. I'm sure Sylvia has dived there. And if you go just inland, we are standing on a fossil barrier reef that extends in parallel to the coast for about 50 kilometers. And it's just one of a few fossilized barrier reefs on that shoreline. If you looked at it, you'd probably think it was a little mountain ridge going along the interior. The fossil coral are spectacular. And if you look at these, on the left, you can see these incredible fossil barnacles on top. It's still attached to the fossil mussels. So we've found and mapped these beaches all around the world from the Earth's most recent warm periods. Stephen mentioned one 125,000 years ago. Here's some more pictures I love. I'm sure every single person in this room has once upon a time had the experience of walking along the waterline at the ocean. The waves come in. They push the air down into the water, and then when the waves go out, all those air bubbles come back up out of the sand, and you can see the characteristic escape holes on the left. We can find beaches around the world where we can see that fossilized in the fossil record. Even in cross-section, the middle lower picture, you can see the escape bubbles preserved. So everywhere we go, almost every continent except for Antarctica, which I'll explain in a minute, we find evidence for past fossil beaches. And we love finding these beaches, and we measure their elevation, and we date them with U-series techniques. But it's not quite as that simple to get at what past sea level was, because the ocean is not a bathtub, and we can't use these fossil reefs and shorelines as bathtub rings. In fact, all of the Earth's surface everywhere is always deforming. Why is that? It is because giant loads of ice are always coming and going, especially in the northern hemisphere, because of the ice ages. Here's the northern hemisphere, what it looked like 20,000 years ago. On the left, a geologic blink of the eye. The Canadian ice sheet was over 3 kilometers thick in its interior. Around the world, the Earth's crust on land and in the sea and on the continental shelves is still readjusting to the melting of that ice. Here's an animation of how that looks. And the redistribution of water and the redistribution of ice. In other words, the bathtub is always deforming. In addition, and this is super cool, this takes thousands of years. That adjustment is still going on. But the water is also never flat. Imagine this. So in addition to the movement of the crust, the ice sheets, when they're there, exert a strong gravitational pull on the ocean. So, and this is instantaneous. Imagine this. And this is the most technical graph I have in my talk. On the left, imagine Greenland is melting. And imagine Greenland is melting such that 1 meter of water, of ice melt, spreads 1 meter of water over all the world's oceans. And this is an entirely plausible outcome by the end of this century, given the path we're on. Okay? Now, if you were anywhere within that red circle, which extends from Norway down to Ireland and across to Nova Scotia, if you lived anywhere in that red circle, even though sea level is rising by a meter, sea level in that red circle would fall. Okay? In fact, it would fall by 10 to 15 meters if you were on the coast of Greenland. Sea level in my home state of New York would rise by only 40 centimeters. On the other hand, if you melted a significant fraction of the West Antarctic ice sheet, which, as you saw, is well underway, such that we had a meter of sea level rise, sea level would fall in the red circle down there, and the sea level would rise much more significantly in what we call the far field. In fact, in New York, sea level would rise by 1.25 meters. So clearly, Europe should be much more worried about Antarctica melting than Greenland melting. These non-uniform patterns of change, they arise due to this gravitational effect on a rotating planet. So, but enough of the complexity, and it is quite complex, the sea level field. Here are some highlights from our studies of past shorelines. First of all, here is Tahiti. Coral reefs. everybody's favorite invertebrate. They grow up to the low tide level, and they're very good at keeping pace with sea level rise. So we can go out on a research vessel offshore and drill down through piles of coral going down hundreds of meters, and we can see the corals that grew and date them at the end of the last ice age, around 12,000 years ago, when the ice sheets were very much out of equilibrium with the Earth's radiation balance and melting quite quickly. And we can see that sea level was rising at a rate of 30 millimeters per year, or 3 meters per century, okay? That's an order of magnitude faster than the current rate of sea level rise, which is 3 millimeters per year. And that rate is double the rate of the 20th century, which was averaged about 1.5 millimeters per year. So Tahiti is telling us what is possible when ice sheets are out of equilibrium with Earth's radiation balance. Okay, if we go back a little further in time to the previous interglacial warm period at 125,000 years ago, Steve Chu showed you it on the ice core record. At this time, the Earth was a little bit closer to the sun due to the precession of the rotational axis of the Earth. And the Earth was thus about 1 to 2 degrees Celsius warmer than pre-industrial time, so about where we are now. On the left is a Landsat picture of Miami. In the middle is a bare Earth LiDAR image, so this is an elevation map with all the buildings and structures and vegetation removed. And you can see that the maximum elevations in this region are about 4 to 5 meters. You can also see all these odd channels, okay, going through the highest elevation part. And on the far right is a modern analog. This is a space shuttle picture of Exuma in the Bahamas. Like the modern Bahamas Bank, 125,000 years ago, nearly all of southern Florida, the southern half of Florida, was underwater, with possibly a few narrow barrier islands built up at the windward Atlantic-facing shelf edge. Sea level globally was about 2 to 5 meters higher than at present. In my last example, I'll show a digital elevation map of the southeastern coast of the US, extending from Florida in the south to Georgia in the north. The characteristic break in elevation, indicated by the dots, is where the shoreline was 3 million years ago. 3 million years ago is how far you have to go back to get to a time that had CO2 levels as high as today, okay, before the Northern Hemisphere ice ages. Globally, and again, this is not from models, but from thousands and thousands of scientists and many more thousands of pieces of data, globally, temperatures were 2 to 3 degrees warmer than pre-industrial, okay? There is stunningly well-preserved shoreline fossils all along this paleo shoreline. In fact, some of the oysters and mollusks we find still have that little papery nacre on the outside. And sea level at this time was at least 12 meters higher than today. There are many places around the world like these places I'm showing you. The evidence is incontrovertible. What does it mean? It means that what happens at the poles doesn't stay at the poles. It means that East Antarctica absolutely is not going to save us. Maybe East Antarctica will grow for a little bit, but inevitably it will turn around too. And there is a lot more melting to come. And also, as Stephen said, that melting is in the pipeline. We've already dialed it in. So today, we can measure that global sea level is rising. We know the rate is accelerating, and we know it's not going to stop anytime soon. And we know that this rise in sea level is essentially irreversible. The 25 centimeters of sea level rise we've seen so far is already a huge problem, and we expect another 25 centimeters over the next 25 years. It's really crucial that we turn this ship. in terms of the polar ice sheets. We know that this 25 centimeters of sea level rise we've already had is already a huge problem. That extra amount of water in the ocean makes storm surges associated with hurricanes and typhoons dramatically more destructive. As you can see, that's from Hurricane Ian on the upper left. On the upper right is Male, the capital of the Maldives. Almost 250,000 people living within a few meters of sea level. It's just one of the many dozens of low-lying coastal nations that are facing the very real possibility of being swallowed up by the seas. And on the lower left is Miami. Again, even today, relentless sunny day flooding can't be stopped by building a seawall because the marine limestone that the city is built on is so porous, the water comes right up through the ground. Miami spends hundreds of millions of dollars on pumps to pump the water back into the ocean, a Sisyphean task if there ever was one. And finally, the sinking city of Venice is obviously a poster child for the difficulty of holding back the sea. So I will end with my own favorite equation. I bumped into this one on a street in Paris about 5 years ago. And it says, knowledge plus action equals power, as well as the future is unwritten. We are running out of time. This is an all-hands-on-deck moment, to continue the boat Titanic metaphor. We need not just individuals to engage, but also governments and captains of industry. We need global systemic change. We need to immediately and rapidly decarbonize our global economy. And we need to do this not just for our planet, but for our children and our grandchildren. For many of us, especially in this room, the most important action we can take, I believe, is raising our voices, and especially something we all can do, which is voting at all levels of government, from local to national. Voting is your superpower. So the future is unwritten, but the future is also now. Thank you for listening.